In this question, you're being asked to synthesize this alcohol molecule with this deuterium hydrogen specifically on that carbon right there. So there's some regiochemistry that we need to consider here. You have to synthesize this alcohol using, you have to synthesize this alcohol using starting materials of 6 carbons or less, and those starting materials must also be alcohols. All right, so again, as usual, we're going to work our way backwards, but we have to consider some things first. And this will sort of help us figure out how we're going to put that deuterium specifically in that position. So we're allowed to start with alcohols of 6 carbons or less. Well, we can see we have a 6 carbon ring here and a 6 carbon ring here. So we're probably going to bring those two things together by using an organometallic like a Grignard or an organolithium. Remember, when those reagents react with aldehydes or ketones, they always make alcohols, which is what we have right here. We have a tertiary alcohol. So we know at some point we're going to use one of those organometallics to react with a ketone, because something like a Grignard and a ketone always makes a tertiary alcohol. And since these are 6 carbon rings, we're probably just going to start with cyclohexanol, since we can start with alcohols of 6 carbons or less. No reason to form the rings, we'll just start with the ring. So since there's 6 carbons here and there's 6 carbons here, we're probably going to make this our new carbon-carbon bond. Okay, so we're going to try to split that thing apart. So we want to work our way back to alcohol here. The nice thing about this one is we're already at a tertiary alcohol, so we can already split this molecule in half. Everything on the left side here from this bond here, everything on the left must have been our electrophile. How do I know that? Because here's the oxygen bonded to that carbon, which means that this carbon must have been the nucleophilic carbon that came in and reduced our ketone. So the ketone that we're starting with here must have been cyclohexanone. Don't worry that you can't name ketones yet. So that must have been the ketone that we started with. And we must have used some sort of Grignard reagent. And it must have been nucleophilic at this carbon right here, because that's where the new carbon-carbon bond is. So I'm going to draw that. I'm going to kind of keep it drawn the same way to sort of help thinking three-dimensionally here. We have our deuterium here. There must have been a magnesium bonded there, and I'm randomly going to choose bromine here, but again, you could have picked chlorine or iodine. All right, let's work our way back from the ketone to the starting alcohol. So we have a ketone here. We have to make that from a 6 carbon alcohol. Well, remember, how can we make a ketone? We can oxidize a secondary alcohol. So let's just draw the corresponding secondary alcohol, which was cyclohexanol in this case. And what reagents do we use to make this conversion? We just need some sort of oxidation reaction. So that's either the Jones oxidation or the PCC method. I'm just going to say PCC here. This is a permitted starting material, so we don't have to work that back anymore. We're allowed to start with alcohols of 6 carbons or less. Let's go back to this Grignard now. So we're just going to ask ourselves, how did we make this Grignard reagent? Well, remember, Grignards are always made from the corresponding haloalkane using magnesium metal in some sort of ether solvent. So I'm just going to go ahead and draw the corresponding haloalkane. The deuterium's still there, and the bromine must have been bonded to this carbon right here. The transformation was made using magnesium metal in some sort of ether solvent. I'm just going to go ahead and say diethyl ether. Well, now we want to make this haloalkane here, but specifically we need that deuterium in that position. So we need to think ahead a little bit. How can we put the deuterium specifically in that position? Well, one way to deliver a specific type of hydrogen is by using hydride transfer reagents, things like lithium aluminum hydride or sodium borohydride. Those things react with aldehydes or ketones to form alcohols by reducing that aldehyde or ketone using a hydride. Well, we have a haloalkane here, so we got to work our way back to an alcohol. We just want to ask ourselves, how can we make a haloalkane specifically from an alcohol? So I'm going to draw that corresponding alcohol, which would have deuterium here, and the hydroxyl group here. How can we make that transformation? It's a secondary alcohol, so we could use things like SOCl2, we could use PCl3, but remember those are SN2 mechanisms. Um, might not work that well, but we can go ahead and just say something like HBr here. We don't have to worry about any sort of shifting occurring because the from a secondary carbocation, it can only shift to another secondary carbocation. So there's no real driving force for that. All right. Well, now we have this alcohol with deuterium specifically at that carbon right there. So how can we deliver deuterium to that position with a high regiochemical control? Well, we could start with the corresponding ketone, which was cyclohexanone, and we want to deliver the hydride to this carbon right here specifically. So how can we do that? Well, we can do a step one where we can use something like lithium aluminum hydride, but deuterated. We want to make sure that our reagent is deuterated with that isotope of hydrogen. Step two would be putting in the acid, the acidic workup. That's in order to put this proton on the final oxygen here. So that'll deliver deuterium specifically to this carbon and then put the hydrogen from the acid on that oxygen. And we've already shown how we can make cyclohexanone from cyclohexanol. So here we have a completed synthesis to make this specific alcohol with deuterium at this specific carbon.